Hello, my name's Simon Tompkins. I'm a senior field application engineer for energy and power at Richardson RFPD. We're a global distributor that specializes in high power applications. I'd like to thank you for joining us on the wideband gap discussion today. Furthermore, I'd like to introduce you to my guest, Ehab Tarmoon, who is staff applications engineer on silicon carbide solutions at Microchip. During this chat, with the help of Ehab, we will explore the advantages of using Microchip silicon carbide power products in high voltage auxiliary E-fuse applications. Hey Ehab, thank you for joining us today.
Hi, thanks for inviting me.
That's great. So could you possibly explain the benefits of solid state devices over conventional approaches, please?
Yeah, and I think I can best illustrate this by showing the difference in a conventional circuit breaker with a solid state circuit breaker under a fault condition. So first, if you consider a thermal magnetic circuit breaker, the graph on the left shows an illustration of its characteristics. So the fault current, the higher the fault current, the faster the response time. So how it behaves under a fault condition. And the graph on the right shows a fault condition showing the current versus time. And so a fault is injected, and you see this in the waveform. The current will rise up until the short circuit current of the system, which is based on the bus voltage and the resistance. And then the contacts of the circuit breaker will open, and arcing could occur, and then the current will drop down to zero. Now, one thing to note is the short circuit current can be very high. It can reach up to 10, 20,000 or even 30,000 amps, depending on the system. Another thing to point out is the current will rise up at a rate of the supply voltage over the inductance. And just with this one example, we're showing that it could reach 20,000 amps within 50 microseconds, assuming a bus inductance or source inductance of a microhenry and 400 volts bus voltage. Okay, so this is just a typical illustration or example of a conventional circuit breaker. Now, the benefits of a solid state circuit breaker or an E-fuse is shown at the bottom of the slide. And you could see by taking advantage of the inductance in the system and the fast response time of solid state devices, particularly silicon carbide, you're able to really interrupt that current and prevent the let-through current and let-through energy from going downstream to your loads and the wiring. And you can interrupt it very quickly and have a very low peak current and help protect the system. Now, something else to point out also is instead of arcing, so there's no arcing involved, there's no separation of contacts, no mechanical separation. So instead of arcing, there's going to be inductive energy that has to go somewhere. You can either put it into a snubber circuit, a clamp, or dump it into the switching device, into the MOSFET.
Yeah, that's very good. Thanks for giving us that overview of the application there. Could you possibly explain how Microchip's silicon carbide offering can enable design engineers to implement solid-state circuit breakers at all?
Yeah, so with silicon carbide, as I mentioned, you get this fast response time, but with Microchip's silicon carbide, in addition to the typical behavior you expect with silicon carbide, we do have superior avalanche capability. So the avalanche I just discussed is one of our strengths. We have a very high single event avalanche rating. In our data sheets, we publish the avalanche energy capability. We also do a repetitive avalanche where we subject the parts to 100,000 UIS or unclamped inductive switching events and test the gate oxide. And we found that we also have a very high and robust and rugged gate oxide when subjected to avalanche, both a single event and repetitive. And so that helps potentially eliminate that snubber circuit that I talked about, or depending on the system parasitics and design, you may be able to minimize the size of that snubber. Another benefit, which is important and critical for this application, is to have a low RDS on, because all the losses are going to be conduction losses. You want to have low RDS on, and we do have the industry lowest RDS on temperature coefficient. It is positive, so you can put devices in parallel to achieve the current rating, but it also is a low temperature coefficient, so it will not increase as much in temperature in RDS on over temperature as our competitors. And you see this in the graph shown here in orange is the Microchip devices. Our 1200 volt family, you're going to have about 45 to 50% increase over temperature, whereas our competitors will be higher than that. We also have a high short circuit withstand time. Our 700 volt family have about 10 microseconds of short circuit withstand time. Our 1200 volt devices are going to be closer to about 2.5 to 3 microseconds. And then a rugged body diode. We do have a rugged and stable body diode. There's no issues with stacking faults or any degradation in the forward voltage or RDS on. And this has been verified by independent third-party testing.
Very interesting. So I guess it's easy to see from the many benefits that it's obvious that Microchip is in a great position, to support the design engineers out there who are developing those types of products, this type of application. I mean, can you perhaps explain whether Microchip have got any typical examples or any reference designs where they can start from to develop their own solutions?
Yeah, so we have the devices, we have the die, the discrete devices, the power modules, and gate drivers in development as well. But in terms of reference designs, we do have a eFuse technology demonstrator. So this is targeting automotive applications, but really can be applied to most DC distribution systems. This is a technology demonstrator targeting 400 volt EVs or 800 volt EVs, and comes in different configurations, 10, 20, or 30 amp current ratings. Now, Microchip, we're known for our PIC microcontroller, so we do have a PIC microcontroller in this, but we also have other technologies. We have LDOs, op amps, the gate driver, and LIN transceiver as well. So we are using our devices in this design. In addition to the silicon carbide MOSFETs, our 700 volt and 1200 volt silicon carbide MOSFETs. Now, this design is available online. If you visit microchip.com/eFuse, there you can find all the design files for this. So the Altium design files, you can get the Gerbers, you can send them out to get built. You have the schematic, the build materials, and the software as well. And user's guide too. So the user's guide has a lot of detail on the design and how to design an eFuse or solid state circuit breaker application for DC systems.
That's great. I mean, it sounds like the technology demonstrator and Microchip, the development of that, you've put a lot of thought into all of the kind of collateral that a design engineer would need to get up and running fast. So hopefully that's clear to everyone to see. But I mean, I guess that we've covered the subject. Thanks, Sihab, for the discussion. It's very informative. So I guess all I can say now is many thanks to all that joined our discussion today. If you'd like to learn more about this subject or any other subject to do with implementation of Microchip silicon carbide power, you could just head over to richardsonrfpd.com, where you'll find lots of information, products, their applications, and the companion products that go along with these types of power products that come from our other suppliers. And with that, thank you again.
Thank you for having me.